yesterday. So today is kind of a combination of what you already know from physics, from pre-cal, and putting it together and getting kind of a cool graph to look at in the calculator and being able to answer questions using the calculator. So, day 2, parametric equation applications, right? That's just the fancy word that math teachers like to use when we're talking about word problems. With the graphing calculator. So grab a calculator if you haven't already. And all of the word problems today are going to be the path of a projectile. In physics, you call this projectile motion. Some quotes there. Projectile motion. So you've sort of done this in a physics setting. Now we're going to do it in a pre-cal setting with a slightly different way. Although some of these formulas should look familiar from physics. A projectile is launched at a height of HO, so that's initial height. Hopefully many of these variables are the same. At an angle of theta with the horizontal, and with initial velocity v0, feet per second. The path of the projectile is modeled by parametric equations. So instead of one equation, or like 7 equations when you had in physics, we're going to use these 2 equations every time. v0 cosine, that's the initial x velocity. So that, I'm going to leave it as v0 cosine, but you might have called it vxi. Or just vx, since it doesn't change. There really isn't an initial and final. It's all vx. Y equals h0, so that's initial height. v0 sine times t, that's vy initial, the initial y velocity, minus 16t squared. That 16t squared is the 1/2 at squared from physics. So hopefully some of this looks familiar. The good news for you is this set of parametric equations will be given to you. So we will give you exactly those 2 equations. Obviously you'll have to know what the variables stand for and where to put the stuff and how to use them, but we'll give you the 2 equations. Alright, number 1. A rocket is launched from the ground at a level angle, or from ground level at an angle of 80 degrees with initial velocity 95 feet per second. Write the pair of parametric equations which describe the path of the rocket. So x of t equals v0 cosine theta times t. So what's v0? 95. The angle is 80, so cosine 80, and then all of that times time. Be careful not to take the cosine of time, right? It's 95 cosine 80 is the coefficient of time. Y of t, h0. So what's our initial height? Pardon? We do know. They didn't give us a number, but they told us what the initial height is. 80 degrees is the angle. That's v0. But I need to know what my initial height is. Ground level. So we have to learn to interpret some of this stuff and put it in the math terms. So 0 plus v0 sine would be 95 sine of 80 times t minus 16t squared. sketch the graph, and write your window settings. Okay, so let's go to y equals. I cheated and already put mine in there. 95 cosine 80 times t. Like, this is fine. If you want to make sure that your parentheses are good, you could put sort of an extra set there. That's a little bit unnecessary, but if it makes it clear to you. Actually, I'm going to get rid of it because I don't like the unnecessary parentheses. But definitely close it after the 80. That way you're only taking the cosine of 80 and then multiplying by t. Same thing with the sine. So I'm going to start with the zoom standard, but that does not look. I don't know what that is. Let's go to window. Let's see. 0 to 360. That doesn't sound like t is in seconds. So I don't know how long this rocket is in the air if you just launch it, but I can't imagine it's in the air for 360 seconds. I don't know. Let's try 10 seconds. And maybe 0.1 for a step. Step is how often the calculator calculates the new point. So the lower it is, the more accurate it is. But the lower it is, the longer it takes. So don't make it, if you make it 0.0001, you're going to have a really accurate picture, but it's going to take forever. So let's try 0.1 and see if that looks good enough.
Is it fine if you use this X max?
Oh, I skipped over something. Mode. You got to do this first. Sorry, go to mode. And you need to be in degree mode because we're doing degrees, but you also need to be in parametric. That's what will give you the x equals and y equals on the graphs on the y equals screen. So go to mode, change it to parametric. Then when you go to y equals, instead of having just a bunch of y equals, you have x equals and y equals. Yeah, I skipped that step because my calculator was already there. Okay, so let me slow down. Is everybody in parametric mode? You see the screen where you can put in the x and the y separately, the two separate parametric equations? Then when you go to window, there should be a Tmin and a Tmax to tell you what times to trace out. I don't really know how far over this thing's going to go, but if we launch it at 95 feet per second, I bet it goes more than 10. So I'm going to start with 100 and see what happens. I'll change my X scale to 10 because I don't want 100 tick marks on my screen. Y min, Y max, I don't know, negative 10 to 100. Like, we're just kind of guessing right now, and then we'll see how it looks. So I'm going negative 10 to 100 for X and Y.
What's the Y scale?
That's Y scale. That's how often you want a tick mark on the Y axis. So it doesn't really matter, but your Y axis looks crazy if you only have one there, because then you'd have 100 tick marks. So I'm going to put a tick mark every 10. Let's see what that looks like. Okay, that's not bad. That's not bad. What do I need to change to see the top of my projectile motion here? I need to change my Y max. I need to go a little bit higher. So 100 wasn't enough. 150 might be enough. Maybe 200 if you want to be sure. Let's see how that works. There we go. I went 200. 150 might have been okay, but 200 definitely worked. Okay, sketch the graph and write your window settings. So, almost all the graphs are going to look like that because it's a projectile motion. But the window settings is what we need to be careful about here. You don't have to make it match exactly, or you don't have to give it the same format as your calculator. You can just say our t went from 0 to 10. Our x went from -10 to 100, and y went from -10 to 200. So that you'll have to play with every time, depending on how fast it's launched and what angle it was launched at. Estimate the maximum height in feet obtained by the rocket. Okay, so let's go to trace. And then you can kind of trace out the path. By the way, you can see that your time is changing by 0.1 every time you go over, because that's what you decided the t step should be. So let's see, what am I looking for if I want the maximum height? The highest number on what? It's kind of an obvious question maybe, but the y value. I want the highest y value. So it's in here somewhere, 136.8. Now it says estimate, so that's good enough. Like if we had made our t step a little lower than 0.1, then maybe we'd be more accurate, but it also would have taken longer to graph, so kind of a trade-off. If you make, while we're here, if you make the t step not low enough, like let's say we really want to go fast, we only want the calculator to calculate every 1 second, then you can still get the shape of the graph, but you also see that's not a very smooth graph, because all the calculator did was take a value every second. And if you go to trace, like you can't trace very much. Like you're really hopping around there. So back to window. I don't want to make this ridiculous, but if we go 0.001, yeah, there you go. It takes forever. You're going to have a super accurate graph. There it comes. Finally. So I don't do that. Like you'd be sitting there forever. So 0.001 was ridiculous. 0.05 maybe. So I'm trying to get a little more accurate without making me wait forever. Okay, 0.05. That's pretty accurate, and I gotta wait a little bit, but not too bad. By the way, it was still, I don't know if you saw this, after it finished the graph, it was still like thinking. That's probably because my t step is farther than it needs to be. If I just go to 6, that's probably far enough. So that was better. By the way, if you don't take your t far enough, so let's say we only went to 3, do you know what's going to happen to my graph? If I only go to 3 seconds, what the graph will look like? It's only going to graph the first 3 seconds. I don't know how long that is, but it's like, well, that's not the end of the graph, but that's all you told the calculator to do. So if you get something like that, then you go back and you're like, whoops, we didn't go far enough on our t. So let's change that back to 6. And so, there's no small part of today is knowing how to play with the window to make your graph look like what you want it to look like. Part D, approximate the maximum range, horizontal distance, the rocket travels. So back to trace. And we want to get all the way over there to where y is 0, where it lands again. This is taking forever because I'm at 0.05. If I'd have gone 0.1, you'd be there a little faster. All right, here we go. So I'm looking at, the question is the horizontal distance, so that's x. But where am I looking at? Which of these values, t, x, or y, am I looking at to know when I get there? Like, how do I know when it's back on the ground?
Y.
When what about y?
Zero.
Well, yeah, when y is back to 0. Okay, so I don't get there, I don't land on 0 exactly, but my closest is negative 0.25. So we'll use that x value, 96.5 feet. This is where you're going to need to be careful if you compare to my answers or you compare to a friend's answers. Because if we use a different step, you might land at a different spot and have slightly different answers here. So it's approximate and estimate, and so it won't be like the last test where I'll be making sure you're accurate to the third decimal, because you'd have to change your step and really mess with it to get there. All right, estimate how long in seconds it takes for the rocket to hit the ground. So that's time. To hit the ground, that's what we were just looking at. So we're already there, but now I just want the time. 5.85. And if your t step had only been 0.1, your answer wouldn't have been 5.85. It'd either be 5.8 or 5.9. All right, let's try number 2. An archer releases an arrow from a bow 4 feet above the ground. So there's H0. The arrow leaves the bow at an angle of 25 degrees, theta, with an initial speed, V0, of 200 feet per second. Write the parametric equations. So x of t equals 200 cosine 25 times t. Y of t equals 4, because our initial height is 4, plus 200 sine 25 t minus 16t squared. Sketch the graph and write the window settings. Okay, I'm going to press pause on this one. You guys see if you can get that into the calculator and then play around with the window until it looks right. Play with the window settings until you get something that works for you. Sketch the graph and write your window settings. Okay. Well, the reason you write your window settings is because all of your graphs basically are going to look like that, right? Because they're all going to be parabolas launched from somewhere, and so they're all going to look pretty close to that. So window settings. I was still 0 to 6 for time. Negative 10 to 1,000 for y, or for x, excuse me, and negative 10 to 150 for y. And so this is another place where if you're checking my answers, we're not going to be exactly the same. If you went to 900 and that was good enough, or you went to 1100, like, it's fine. And our y values could be different as well.
Whenever we find like for it to hit the ground, we do the negative number. And it's like, if 2 is closer to 0 than negative 6 is.
Yeah, just get to the y value that's closest to 0. And maybe it's slightly above 0, maybe it's slightly less than 0. Just pick the closest one. Alright, maximum height. Let's see. Okay, I'm looking for my y value. Which one is biggest? 115.6. A couple places it's 115.6. And because of the rounding, I don't want to give 3 decimals because I really doubt that's accurate to 3 decimals.
I got 517. I don't know how. I changed my X to 2000.
Assuming the ground is level, estimate the horizontal distance. So that's where we just come all the way over and wait till y equals 0. But the answer is whatever x is. So I'm looking for where y is 0, or as close as it'll get, because again, we only calculated every 0.05. And so, let's see, 2.5 or negative 1.7. So I'm going to go with the negative 1.7, and my x value is 969.7. Yes, sir.
So I don't have that value on mine, right? So like whenever you're grading,
Yeah, I'll have like a range there, because if you pick different T-mins and T-maxes, or a T-step is really what will affect like how fine-toothed that number is. So, yeah, the key will have like a range that's, I don't know how wide the range will be, but if you're in the ballpark, you'll be fine. Right? If you've got 700 there, that's not in the ballpark.
Yeah.
All right, flip it over to the back. This is a fun problem here. A baseball is hit in Minute Maid Park at a point 3 feet above the ground, right? Because that's about 3 foot high off the ground where the ball comes in. It leaves the bat at an angle of 24 degrees, launch angle, right, Cole? With an initial velocity of 92 miles per hour. So that's not like a Yordan Alvarez smoked ball, but that's hit pretty hard. Heading toward left center field, where the 25-foot wall stands 375 feet from the plate. We got a little picture here. I'm going to write the set of parametric equations describing the situation. But there's a little trick in here. 92 miles an hour, but we don't really want miles per hour. We want feet per hour. Actually, we don't even want feet per hour. We want feet per second. So job 1 is 92 miles per hour into feet per second. So this is the old chemistry train track thing. You try to make all the units work out. It's my favorite part of chemistry, because I didn't have to know chemistry to make it work. So I need the miles to cancel, so I'll put miles in the bottom, feet in the top, and then it tells me right here there are 5,280 feet in 1 mile. So miles are gone, and now I've got feet. I want the hours to cancel, so I'll put hours in the top. And I think I can go all the way from hours to seconds, because I know how many seconds are in an hour. 3,600 seconds in an hour. So 92 times 5280 times 3,600. Whoops, I didn't do that right, because that looks really big. 92 times 5280 divided by 3,600 would be a better way to go here. 134.93. That's my V0. And rather than have to type that in all the time, we've done this before, I'm going to use the store thing. So I'm going to store that. So STO, bottom left. You can call it whatever you want, but since it's my velocity, I'm going to call it V. And now anywhere in the calculator that I type V, including on the graphing page, that's what it'll be. So this is going to look pretty cool, or look clean when I go to put that in for my graph. Okay, write the set of parametric equations. X equals V, since I called it V, cosine 24 times t, and y equals 3 plus v sine 24 times t minus 16 t squared. So we go to y equals, and now I don't have to type in the weird number for v, I can just type in v. Cosine 24 times time, and 3 plus v sine 24 times time minus 16 t squared. And then my graph is probably wrong, although not terrible. At least I can see everything, but I would like a better picture than that. The wall is 375 feet away, so that's a pretty good clue on x. I'll go to 400, that way it's probably enough. My y didn't look like it needed to be 150, so I'll back it down to 100 and see how that looks. So again, you're just kind of playing with it and see if that works. Okay, I can't quite see everything, so maybe I want to back up a little bit and make my x max a little bit bigger. How far would this ball have traveled? There we go. Sketch the graph. Again, it's sort of like all graphs look the same because they're all projectile motions. So t was 0 to 6, although it probably didn't need to be that long, but that's fine, it's already done. X was negative 10 to 450. Y was negative 10 to 100. There's my picture. All right, does the ball go over the wall? Okay, well the wall is 375 feet away. So it definitely goes farther than 375. The trouble is the wall is 25 feet high. So when my x is 375, I need to figure out what y is. Right? Because it goes farther than 375, but I need to know the height of the ball at 375. So I'm looking at my x until it gets to 375, or as close as I can get it. Well, that's pretty close. 375.9 or 376. So 376 feet away, my height is 21.6. So am I over the wall or not over the wall? I am not over the wall. Not over the wall. Because the wall is 25 and my height is 21.6. So no, we did not clear the wall.
So where did you get the 375 from?
Because it told me that the wall is 375 feet away.
Oh.
So I needed to know what's my y value 375 feet away, because I want to see if I've hit a home run or not. All right, part D, change the launch angle to 25 degrees. Does this change the outcome of the at-bat? Well, so go back to y equals 24, or change 24 to 25. So now we got a little more launch angle, so it launches a little bit higher. Let's see what happens. The window still works because it's pretty close to the same thing. And here we go tracing again. So I'm looking for the same thing. when x equals 375, or as close as I can get to it, without changing my t step to something ridiculous. Scrolling. So t equals, well, I can't get to 375 exactly, but whether it's 372 or 379, either one of those, the y value is over 25, so I'm good. So I guess 372 is a little closer. Y equals 28 feet, so home run. Home run or not, based on 1 degree of launch angle. It's almost like I knew that ahead of time and planned that problem out to work that way. All right, assignment today is worksheet 2. This is one there, the worksheet might take shorter than the notes.